Statistical methods that are commonly used for the analysis of questionnaire data that is based on Likert scale or continuous scale. The first multivariate statistical analysis is the principal component analysis, abbreviated as PCA. The second one is the exploratory factor analysis, abbreviated as EFA, and the third one is the confirmatory factor analysis, abbreviated as CFA. Principal components analysis, abbreviated PCA, for analyzing data extracted from a questionnaire or a survey. In this presentation, description of the PCA will be provided, and the common uses of the PCA will be mentioned, and the assumptions that have to be fulfilled before performing the PCA will be listed, and a short description how to input the data into one of the statistical software, and finally how to interpret an output from a PCA. Principal component analysis is a multivariate statistical techniques or a method that deals with data that consist of multiple variables or multiple items. It is an unsupervised statistical method. The objective of performing PCA is to reduce the number of variables in a data set. So it is dimensionality reduction method. It aims to reduce larger number of variables that is extracted from a questionnaire or a survey. Variables are items or questions. The objective is to reduce this large number of variables into a smaller number of variables that are, or a smaller number of variables grouped together, and these groups are called principal components. So the objective from performing the PCA is to reduce the number of variables and arrange these variables into groups called principal components. These components explain most of the variance in the original variables or data. Items within these components or variables or questions are correlated. The overall objective from performing PCA is to have a large number of items or variables. Try to reduce that number by grouping those items or variables into components. These components or variables within these components are correlated to each other. So what are the common uses of PCA? When a researcher start to design a new questionnaire or an instrument or a scale, then a PCA is a useful statistical method. The objective of performing that method is to check if all or some of the items load into construct. If some of the variables are not sufficiently representative of the construct or the section within the survey or the instrument or the questionnaire, then remove those variables from the measurement scale. So PCA can be used when designing a new questionnaire to check which items loads into certain sections or construct within a questionnaire, and those that they do not load to this construct, or they do not correlate with the variable within that construct, then remove that item or variable. The second use of PCA is to reduce the number of variables in a construct. So it is called construct PCA. If a construct consists of, let's say, up to 12 variables, then PCA can be performed to find out what variables within that construct, which is part of the questionnaire, that are highly correlated and represent the construct. The third use of the PCA is to shorten questions to be included in the questionnaire. Shorten these items or questions or variables into fewer items. So another objective is reduction. So if more than one item measuring same construct, then remove that item, and that will help to design a scale or an instrument that can be accomplished and completed by participants. So what are the assumptions that have to be fulfilled before performing PCA? The first assumption is that multiple variables are measured at a continuous level or ordinal. So the data or the responses collected from participant completing the questionnaire, it can be an ordinal based on 5 Likert scale from 1 to 5, or 7 or 9, and so on. Or the responses can be a continuous variable. So there should be a linear relationship between all variables if they are continuous. PCA is based on Pearson correlation coefficient. The method also can be used for ordinal data such as Likert scale. Linearity can be tested using a matrix scatter plot. The second assumption is sampling adequacy. There have to be enough number of participants. There have to be 5 to 10 participants per question or per items as a minimum sample size. Using rule of thumb, 10 participants per question can be considered. And the way to check, or the method to check whether there is a sampling adequacy, is to perform a Kaiser-Meyer-Olkin sampling adequacy that will measure the sampling adequacy for all overall data sets. The third assumption is that the data should be suitable for data reduction, sufficient correlation between variables to reduce variable to a smaller set of components. Though there should be a correlation between items, that correlation has to be within a certain values from 0.3 to 0.8. The Parlet test of sphericity can be performed to test this assumption. The fourth assumption is that there is no significant outliers, and the fifth assumption is independent variables are correlated to each other. Another assumption is that principal components are assumed to be independent of each other. And finally, there should be a homoscedasticity, in which the variance of the data is constant across all level of the independent variables. In this slide, a print screen from a SPSS software has been inserted here. When performing PCA in SPSS, the following boxes need to be ticked. First of all, the correlation matrix, tick for the coefficient for correlation and the significance level for correlation, the determinant, which is an important values for testing the data and whether it is enough to be used for performing PCA, and also tick for the KMO and a Bartlett test of sphericity for sampling adequacy. The next slide gives options for selecting the method for analysis, which is the principal component analysis, and the eigenvalue is selected to be greater than 1. For performing the PCA, the method for rotation has to be decided in advance. There are two types of rotation. That depend on the variable, whether they are correlated. If the variables are correlated, then the direct oplimen will be used or the pro max. When the variable are not correlated, then the method to use for rotation is orthogonal, and there are several methods: varimax, equimax, and quantimax. The output that will be generated from the PCA analysis, there should be important things to look for. There is no missing scores. To check for the correlation coefficient, which is the R, the Pearson correlation coefficient, the value for determinants, and the KMO and Bartlett test for sample adequacy and sphericity, the setting for the eigenvalues, the total variance, the scree plot, the values for communalities, and the rotated matrix, with finally the table for the component transformation matrix. So this is a table extracted from a PCA analysis in which a correlation matrix has been generated for 9 items, item number 1 to 9, and the correlation between pairs of these pairwise of these items is given here, with statistically significant values shown here. And as shown here, that there is a perfect correlation between item 1 and item 1, and with item 1 and 2 the value is 0.65, and with item 5 and 1 it is 0.02. For the correlation values need to be, which is the R, need to be less than 0.8 and greater than minus 0.8. And the determinant has to be greater than 0.40 and 1. The next slide shows an output for the KMO and Bartlett test. The value need to be for sampling adequacy to be greater than 0.5, and ideally anything greater than 0.5 will be acceptable, but the higher the better. The p-value should be less than 0.05, and for the eigens values when performing the PCA, the eigenvalues set out as greater than 1. So what does this eigenvalues mean? It represents the variance explained by each principal component. Higher the eigenvalues, the more variance is explained by the principal component. Here is a table extracted from a PCA analysis. As shown here, the total variance explained. There are here 8 items, and as shown in the section here, extraction method, principal component analysis, there are 8 items, and those items have been grouped into 3 major components: component 1, 2, and 3. Component 1 explains 27.3% of variance. The second component explains 25.7%. The third is 19.1%. The 3 component explains 72.2% of the variance. The next slide shows the scree plot. Scree plot assists in determining the appropriate number of principal components to retain or to obtain from the analysis. It is used to visualize the eigenvalues and identify the point at which the curve levels off, suggesting that the optimal number of components to retain. Here in this graph, it shows that on the x-axis is the component number, on the y-axis is the eigenvalue. There, the cut point for the eigenvalue is 1, and there are 3 major components, 1, 2, and 3. The next slide describes a terminology called communalities, which is a table generated from the PCA analysis. Communality is the proportion of variance in each variable that is retained in the principal component. So the value for the communality ranges from 0 to 1, as shown here in the table. The first item has a communality value of 0.8, the second 0.7, and so on. The next slide describes factor loading. Factor loading is a measure indicates the strength and the direction of the relationship between variables and principal component. The higher the factor loading, the stronger the relationship. Factor loading is a coefficient, and the cut for factor loading as a rule of thumb is 0.3. Some people use 0.4, and some people become more stringent and use 0.45. So aim for a high value, which is 0.9. As shown here in the table extracted from a principal component analysis using a varimax method for rotation, these 9 items has been grouped into 3 components, component 1, 2, and 3, as shown in this rotated component matrix. The first component have 3 items. These 3 items, item 4, 6, and 5, loads together on that component, and the loading factor score is 0.88, 0.7, and 0.7. So those 3 variables loads into that component. For the second component, there are 3 items. Item 1, 2, and 3 loads into the component 2, and the value for the factor loading is 0.9, 0.8, and 0.79. And finally, the third component have 3 items loaded into it. Item 7, 8, and 9. With the first one is 0.89, 0.7, and 0.65. All these 3 items load into the component principal component 3. So the overall analysis from the PCA has managed to group these 9 items into 3 components. Another output that can be generated post PCA is the component transformation matrix. The component transformation matrix will look at the correlation between component number 1 correlation with 1, and 1 with 2, and 1 with 3. So if the components correlate to each other, then this will help in determining the rotation method. then use oblique rotation, whether it's direct, oplimin, or pro-max. When the components are not correlated, then use orthogonal rotation, such as varimax, equimax, and so on. And how do we determine the cutoff point for correlation or no correlation? A value of correlation between two components of greater than 0.32 indicates correlation between the components. Exploratory factor analysis, abbreviated as EFA, for analysis of data that is taken from a questionnaire or a survey. EFA is called also principal factor analysis, PFA, or principal axis factoring, PAF. PCA is the first phase of EFA. So when you have a data, the first step to do is to do principal component analysis. Then EFA can be done. EFA is a multivariate statistical method, a method that analyzes data that consist of multiple variables, few variables. It is commonly used when developing a questionnaire or a scale or an instrument in which there are multiple questions or items in the questionnaire, and each item or question represent a variable, and then the EFA is the method to use for the analysis of these multiple variables. The EFA is a statistical method used to uncover the underlying structure of a large set of variables. When there are large number of items or questions, then EFA will try to discover the underlying structure for these items, whether they can be grouped and loaded into a specific construct or a factor. It aims to identify a set of latent construct that underlying the measured variables, whether the group of variables measure certain construct or factor. EFA is an exploratory method that will explore whether large number of measured variable or observed variable related to a small number of unobserved factors. It aims to identify the underlying relationship between measured variable. Try to find out whether there is a correlation between variables. It assumes no prior relationship among factors. So there is no correlation between factors, but there might be a correlation between certain items that might load or measure a specific construct or factor. So the EFA will determine factors that explain common variance, which is correlation of a set of variables. It helps to understand how many factors can be present in the data. So it can section the data or the variable into groups, and those groups are called factors. It helps to identify underlying factors among survey questions, items, variables, the same terminology. The next step once the EFA is done is to perform confirmatory factor analysis. So what are the assumptions that have to be fulfilled before performing this statistical method? First assumption is that there should be adequate number of participants. Sample size have to be adequate, and the participant has to be greater than 150 individuals. More than 150 cases or individual or participant. At least there should be 20 participants per items or per variable or per question. One of the statistical methods that can be performed to find out whether there is adequacy in the sample size is to use the statistical method for Kaiser-Meyer-Olkin method. It will be given a value. Any value closer to 1 indicates better sampling adequacy. The second assumptions that have to be fulfilled is the eligibility of correlation matrix for factorization. The third assumption is linearity. There should be a relationship among variables, and those relationships are linear. So observed variables are related to the underlying factor in a linear manner. The fourth assumption, there is no perfect multi-collinearity among variables. So variables, they should not have a high value of correlation or relationship. The fifth assumption is the normality. Though EFA is robust to violation of normality, variables should be approximately normally distributed, and if variables are not normal, then transformation for the data can be performed. The sixth assumption is the interval or ratio level of data. The data should be interval or ratio. For ordinal data, there should be more than 5 categories, and for categorical variable, then the best option is to go for categorical factor analysis. The seventh assumption is the homoscedasticity, which is equal variances. The variances of the observed variable roughly equal across all levels of underlying factors. The eighth assumption is that there is no outliers. Outliers are extreme high or low values within the data. The ninth assumption is that EFA assumes that the observed variables are influenced by two things. The first one is the common factor. The second one is the unique factors. Common factors are shared variance among variables, and unique factors are specific variance unique to each variable. And number 10 is the independence of factors. The EFA assumes that factors extracted are uncorrelated. If the factors are expected to be correlated, then confirmatory factor analysis can be used. Before performing the EFA, the factor rotation method has to be determined. Decide on appropriate rotation method and then run the analysis. There are two types of rotation. When the anticipated factors are correlated, then go for oblique method. Oblique method can be a direct Opperman or Promax. When the factors are not related, then orthogonal rotation method can be used. There are subclasses for it: Varimax, Equimax, and Quatrimax. When performing the EFA on a data, a correlation matrix will be produced, and the items within these matrix all should be analyzed via bivariate correlation matrix. The value for the correlation coefficient, which is R, should be between less than 0.8 and greater than minus 0.8. Higher correlation coefficient values greater than 0.8 indicate multi-collinearity. In this situation, the item or items have to be removed. So remove one pair of items with bivariate correlation coefficient score greater than 0.8. When the R value is less than 0.3 or greater than minus 0.3, then omit that item from the analysis. There is also another value determinant, which is called the determinant of the correlation matrix. So here is a output for the correlation matrix performed using EFA on 6 items, item number 1 and item number 6, from 1 to 6. The top section is the correlation, pairwise correlation between items, and the bottom section is the significant level, and at the end here is the determinant. So for the correlation, when item 1 is correlated with item 1, it is perfect correlation. Item 1 correlates with item 2, the value is 0.65, which is within the range. For item 3, within the range. Correlation between item 1 and 4 is very poor, less than 0.3, it is 0.03. So this item number 4 is weakly correlated with item 1, and item 1 and 5 is less than 0.3. So the correlation value between pairwise items need to be examined and checked, and the p-value is given here, should be less than 0.05 for significance, and the determinant have to be greater than 0.40 and 1. The next step is to check the sample size adequacy. So to check sample size adequacy, use the KMO statistics as shown here. The sampling adequacy is given a value in this table, it is 0.6, and the p-value is less than 0.05. So the minimum acceptable score for this test is 0.5. Anything above 0.5 is considered to be enough data or sample size to perform the EFA. The p-value has to be less than 0.05. What is also important that has to be checked and examined is a term called communalities, that is calculated post performing the EFA. Communalities refer to the proportion of variance in each observed variable that can be explained by the factor extracted, or the latent factor extracted. So the value for communalities indicate how much of the variability in the observed variable that can be explained by the extracted factors. The values for communalities ranges from 0 to 1. Higher values indicating more common variance. Higher communalities indicate that a larger proportion of the variability in the observed variable is accounted by the factors. And this suggests better fitting of the model to the data. So variables with low communality may not be well represented by the factors and may need to be excluded from the analysis. So when there is a communality value of less than 0.3, then omit the item and perform the analysis again. Here, as shown, an extract from EFA output analysis. Communality has been calculated at the initial and after extraction for item number 1 to 6. Item number 1, the communality is very high, 0.91, and for item 2 it's 0.47, item 3 is 0.43, item 4 0.96, item 5 and 6 0.3, and so on. So there is no communality less than 0.3. Examining the communality value is essential for performing the EFA. There is another term that has to be checked when performing the EFA, which has to be determined prior to performing the analysis, which is eigenvalues. eigenvalues help to determine the number of factors to retain in the analysis. The value for this indicates the amount of variance explained by each factor. Usually, by default, the eigenvalue is set at a value greater than 1, and the eigenvalues will generate a table, and that need to check the proportion of the total variance explained by the retained factors, and this proportion has to be at least 50% and greater. The eigenvalues can help in optimizing the number of factors and then determining and fixing the number of factors to extract and perform the rerun of the analysis. In the next slide, an extract from the EFA analysis for 6 items has been placed, and a table is generated for the total variance explained. Here we have 6 items and only 2 factors has been extracted, factor number 1 and factor number 2. Factor number 1 can explain 35.9% of the variance, and factor 2 34.1% of the variance, and both of these factors, the accumulative percentage, they can explain 70% of the total variance. So the EFA managed to extract 2 factors out of these 6 items, or sort out these 6 questions or 6 items or 6 variables into 2 major factors, factor number 1 and factor number 2. Both of them can explain 70% of the variances. If we move to the next slide, a plot has been generated. It's called scree plot and placed in this section here. On the x-axis is the number of the factors that can be extracted, and on the y-axis is the eigenvalue. And since we had set the eigenvalues to be greater than 1, as shown from the scree plot, there are 2 factors that have been extracted following the certain criteria set for the analysis. Scree plot is a graphical tool to determine the number of factors to retain in EFA. There is another also value that need to examine, which is called factor loading score or value. Factor loading is a correlation between item and a factor. So it is a correlation coefficient between a variable and a factor. So a score will be given or a value, and it's called factor loading. The value shows how much the variable is influenced by the factor. The factor loading value, it is the value that indicates the strength of the relationship between the items and the factors. Larger values indicate stronger association between observed variable and the underlying factor. So factor loading values ranges from -1 to 1. Value close to -1 or 1 indicates a strong correlation. Values close to 0 indicates a weak influence. Positive value indicate positive correlation between variable and a factor. Negative values indicate a negative correlation. So variable with a high loading on a particular factor are considered to be strongly related to that factor and are often used to interpret and label the underlying construct. So factor loading score is an essential values that will help in determining whether the items load into the factors. The higher the value for the factor loading, the stronger the correlation between the variable and the factors, and this will help eventually to identify and label this factor or this construct extracted. The cutoff point for factor loading usually taken is either 0.3 or 0.4 or 0.45, and the way is to delete the items that have no loading or doesn't load into any factors, or have a value of less than 0.3, and then the test has to be rerun. So look for any factors that have at least 3 items with a loading greater than 0.3 or 0.4 or 0.45 and low cross loading. So the cutoff point for the factor loading can be determined whether it's 0.3. Some researchers prefer 0.3, some researchers make it more stringent and use 0.4, and others even more stringent by using the cutoff of 0.45. Remove any items with cross loading of greater than 75%. Start with one with the lowest absolute maximum loading. So remove the items that have the lowest absolute maximum loading. In the next slide, a table is extracted from an output performing EFA, exploratory factor analysis, with a rotation method Opleman, and a pattern matrix is generated as shown here. There are 6 items, item 1 to item 6, and there are 2 factors that are extracted based on this method, factor 1 and factor 2. Factor 1, there are 3 items that load into that factor, 3 items that measure that factors, item 1, item 2, and item 3. The factor loading value is 0.95 for the first one, 0.68 for the second, and 0.64 for the third items. So all these 3 items have a higher score for factor loading, and they all 3 load together into that factor 1. For factor 2, item number 4 and 5 and 6 load into that factor with a factor loading score of 0.98 for item 4, 0.62 for item 6, and 0.57 for item 5. So all these 3 items load into that factor number 2, and the value for factor loading is sufficiently high, and the cutoff point was taken as 0.3, so there is no values below than 0.3. So the factor loading examination or checking in EFA is essential to determine whether to retain or remove item or items from factor or factors that do not load sufficiently into the factor, and they don't have a high factor loading greater than 0.3. Confirmatory factor analysis, abbreviated as CFA, for data extracted from a questionnaire or a scale or a survey, or even to develop a measurement which is based on a Likert scale. In this video, I will first define and describe the confirmatory factor analysis, and then I'll move to mention and list assumptions that have to be fulfilled before performing the CFA, and then I will describe and list some of the application of CFA before finally describe the steps that have to be followed to perform confirmatory factor analysis. So what is CFA? CFA is a special form of factor analysis. So it is part of factor analysis, as factor analysis can include principal component analysis, exploratory factor analysis, and confirmatory factor analysis. So exploratory factor analysis, EFA, will identify the underlying latent factors from the items or variables included in the analysis from a data taken from a questionnaire or a survey. So CFA is used when there are prior knowledge about the structure of the variables, the relationship between items or variables, and which items measure or represent factors. So first of all, EFA has to be done to sort out and assort and group items into factors, and then the CFA can be performed. So once EFA is done, then the CFA can be performed with a new set of data. So once this new set of data are collected, then the confirmatory factor analysis will examine and confirms structure or structures of latent factors produced from the EFA. So EFA will generate a model, a structure for the data by sorting them out or arrange them into groups called factors or latent factors. Each factor will contain a number of items or variables that measure that factors. Then the confirmatory factor analysis will confirm or disconfirm the output from the EFA. So first EFA has to be performed, then the CFA. The CFA is a complex approach that tests the hypothesis that the items are associated with specific factors. So it is an approach that you have already a pre-established, pre-known model for the data, factors and their associated items or variables. So CFA is hypothesis driven. It is used for testing a pre-established hypothesis. This hypothesis will describe the structure and the relationship between observed or measurable variables and the underlying latent factors. So the aim or aims from the CFA is to confirm or disconfirm factor structure based on prior knowledge, prior analysis from the EFA. So it tests whether the data fit a hypothesized model that describe the structure of the factors and the items that associated with that factor. So CFA will impose a structure on the data and check how well the data fit this pre-specified factor structure or model. In CFA, the number of factors are already specified, determined, known in advance, as it has been determined by the EFA, Exploratory Factor Analysis, with variables that load on each factor. So we know the number of the factors and the items that associate or load or measure that factors, and the relationship between factors and their observed or measurable variables. The CFA will validate this theoretical model and assess how well the observed data, the new collected data, fit the proposed model that is proposed from the EFA. So researcher or statistician will specify the theoretical model with hypothesized relationship between latent factors and observed variables. So CFA will test how well a pre-specified factor structure are confirmed by the observed data. So it can test the latent factors are correlated in the model. So it can also not just test whether the items are associated with specific factor, it also can test latent factor can correlate to each other, or i.e. latent factors covary. So the CFA uses the structural equation modeling, which is SEM, to test a model whereby loading into that factors allow for evaluation of the relationship between observed variable and unobserved variable. So to recap, CFA is a following step post doing EFA. In EFA, the number of factors and the items that measure or load into the factor or factors will be already determined through EFA. Then the CFA will use a new set of data to test that model and to test whether these items fit into that factors and there is a relationship between the items and factors. In this slide shows the factor structure, i.e. the model proposed by the exploratory factor analysis. Here, as shown, there are two factors, factor 1 and factor 2. Factor 1 loads into it 3 items, and factor 2 loads into it 3 items, and factor 1 and factor 2 can co-vary. So there is a loading for each item to that factor. So this is the structure of the model that can be proposed or hypothesized or determined by the EFA to be tested in the confirmatory factor analysis. CFA can be used for validating measurement instruments when designing a questionnaire or a scale or a survey. Then the CFA can accurately assess the intended latent construct. So for validating survey or questionnaire, assessing construct validity, that's one of the applications of CFA, testing theoretical models, and identifying relationship between variables or items if it is a questionnaire or a survey. And also it can play an important part in scale development and refinement, as there is an option for removing some of the items that load into factors, so that there is a chance for a possibility for development of a questionnaire or a scale. It can be used also for quality assurance, for market research, educational assessment. Other applications of the CFA is to perform confirmatory analysis in mixed method research, in which there are qualitative and quantitative data. Also, the CFA is very vital for clinical assessment and diagnosis to develop tools for testing. So what are the assumptions that have to be fulfilled or satisfied before performing the CFA? The first assumption is the multivariate normality. Since the CFA look at several variables or several items, so it is multivariate analysis. So it have to be a multivariate normality. Assumes that the data follow multivariate normal distribution and variables are normally distributed both individually and jointly. The second assumption is linearity. Assumes that the relationship between observed or measurable variables and the latent factors or construct are linear. The third assumption is no multi-collinearity. The observed variables should not be highly correlated with each other, i.e. items within factor or factors should not have a high correlation value or coefficient. The fourth assumption is absence of outliers, outliers are an extreme high or low values in the data that deviate from the rest of the data. The fifth assumption is the reliability and validity of measurement. It assumes that the observed variable are reliable and valid measures of the underlying construct or factor. The sixth assumption is that there should be sufficient sample size. Relatively large sample size to produce reliable estimates is needed. So the sufficient sample size should be greater than 200. The seventh assumption is the independence of observations, which assumes that the observations are independent of each other. The eighth assumption is that there should be a correct prior model specification. There should be a model with known factors and known items that load to each specific factors. So assumes that the specific model correctly represent the relationship among the observed variables and the latent factors extracted from an output or an outcome from the exploratory factor analysis. The ninth assumption is the absence of measurement error. The assumption states that they should assume that the observed variable are measured without error. The 10th assumption is the normality of residuals, that assumes the residuals, which is the difference between observed and estimated values, are normally distributed. And the 11th assumption is the data must come from random sample. So to perform the CFA, several steps have to be followed. The steps to assess the fit of the specified model to data. So we've already had a model which is obtained, generated from a previous analysis. Then the way to assess whether the data fit that specified model. There are several steps. The first step is to define the research objective and hypothesis. The objective is the primary goal of CFA is to assess the fit of the hypothesized factor structure or model to the observed, measurable, or obtained data, a new set of data. The hypothesis states that or formulated about the relationship between observed variable and latent factors. How many factors are there? Which items associate with which factor and load to the factor? And the CFA is then used to confirm or reject the theoretical model proposed by a previous analysis through EFA, which indicates can be accepted or rejected based on the outcome of the CFA analysis. The second step is to prepare the data. You need to screen the data and examine the data for missing values, outliers, and distributional assumptions. Data meet the assumption of multivariate normality, and transformation is done if assumptions are violated. So if the data does not follow normally distributed, that's a violation of the assumption. The alternative way to resolve that is to transform the data. There should be also no missing data when screening the data to perform CFA. And a way to deal with missing data through imputation. For a missing data, add the median or the mean according to the data type. Variable selection include the variables that are theoretically relevant and have a meaning factor loading. So just only include items that measure or load to a specific factor as determined by the exploratory factor analysis. The third step is to specify the model. Define the latent factors and their observed variables. Specify the relationship between the latent factors and observed variable, which is the factor loading. So you need to specify the model, build up the model as shown previously in the slide, which shows the model, the structure for the factors and the items loading to each factor. Draw the model. The next step is to estimate the parameter. Parameter estimation is that they estimate the model parameters, including factor loadings, variances, and covariances, and to select fit indices and to choose the appropriate fit indices to evaluate how well the model fit the data. So common indices that can be used and are commonly used are the chi-square, the Comparative Fit Index, which is abbreviated as CFI, and the Tucker-Lewis Index, the Root Mean Square Error of Approximation, which is RMSEA, and the Standardized Root Mean Square Residual, SRMR. So these are some of the indices and the most common indices that can be used to determine whether the model fit the data. So then the next step is to run the confirmatory factor analysis using statistical software, whether R statistics, whether AMOS, and any other statistical software. So there is a software which is part of the SPSS called AMOS that can perform that analysis. So use this software to estimate the parameters for your CFA model. Review the output for factor loading, standard errors, and modification indices. Then evaluate the model fit. This is a giant step that need to be taken cautiously, as this will determine and assess how well the proposed model fits the observed data by examining the indices and comparing observed values to recommended thresholds for good fit. So some of the indices that can be used for assessing the model fit is the chi-square test, C-min divided by DF. The second one is root mean square error of approximation, which is abbreviated as RMSEA. The third one is standardized root mean square residual, SRMR. And the fourth one is Brown codec criterion, PC. And the fifth one is Comparative Fit Index, CFI. The sixth one, Pentler's Comparative Fit Index, PCFI. And the seventh is Parsimony Comparative Fit Index, PCFI. The eighth is Goodness of Fit Index, GFI, adjusted GFI. The ninth is Normed Fit Index, NFI, and Non-Normed Fit Index. The 10th is Cake Information Criteria, AIC. The 11th is the Bayesian Information Criterion, PIC. And the 12th is the Expected Cross Validation Index. So those are the most listed indices that is generated as an output from CFA analysis. Not all of them are considered. The most common one will be described later on. So to assess the model fit is first of all to perform chi-squared test. As shown here, the CMIN is the minimum fit function chi-square statistics. Chi-square statistics goodness of fit statistic is performed to assess how well the proposed model fits the measured or observed data. So low value of Spearman indicates good fit between the proposed model and the data. High values, on the other hand, suggest a poor fit. So the measurement Spearman is sensitive to sample size. Usually the chi-square is divided by degree of freedom. Spearman divided by df should be less than, equal to, or less than 5, and the significant level should be greater than 0.05, so it should be no significance, as the null hypothesis states that the model fit the data, and the alternative hypothesis states that the model does not fit the data. So this is a description and a list of an output generated from CFA analysis. As shown here, that's the degree of freedom is 8, the chi-square is 27.4, and the probability level is less than 0.05. So here this is an indication that the model is not best fit the data, as shown in the next slide. The default model, as shown in Spearman, is 31.5, df is 8, degree of freedom. When this value is divided by the 8, it will generate 3.8. So this is okayish value, but the p-value here is significant, and the NPR stands for number of parameters for each model. The next index is the Fmin, stands for the index of the model fit. It is used and reported when the Spearman does not have the positive result, usually caused by a large sample size. The Spearman is described with boundaries expressed by low and high. Lower and higher boundaries of 90% confidence interval for Fmin. Value for Fmin close to 0 represent better model fit for observed data, 0 value being the perfect fit. So the next slide shows a table extracted from CFA from Amos for model fit indices, and as shown here, the Spearman is given here, and the lower boundaries for 90% and higher boundaries is given here, and the Spearman value fit between these lower and higher. The next index is the Holter index, and as shown here, Holter index is a measure used if the chi-square is significant or not. So Holter 0.05 measure if the sample size is higher than the value specified for the default model. At 0.05, the default model should be rejected. For Holter 0.01, calculate if the sample size is higher than the number of specified for default model at 0.01 level. Default model may be rejected. The next index is the root mean square error of approximation, RMSEA. The index measures how well the model fits the observed data. The value for that index is ranging from 0 to 1. Smaller values indicate better model fit. To interpret the RMSEA values, any value less than 0.05 is excellent fit. Between 0.05 and less than 0.08, good fit. Between 0.08 and less than 0.1, acceptable, and any value equal to or greater than 0.1 is a poor fit. As shown here in this table, the RMSE value is 0.12, so it is a poor fit, and the lower boundaries, the higher boundaries, and the p-value for the null hypothesis is given here. So this value should be less than 0.05 to be excellent. The next index is the standardized root mean square residual, SRMR. The index will assess the goodness of fit of the structural equation model. It will provide the measure of discrepancy between observed correlation and correlation predicted by the model. So the value represent the average difference between the observed and predicted correlation, with smaller values indicating better model fit. So the value for it ranges from 0 to 1. Any value less than 0.08 is an acceptable model. The next index is the Brown-Kodak criterion, PC, is an alternative to RMSEA and SRMR. The value close to 0 indicate better fit. The next index is the Comparative Fit Index, CFI, is a statistical measure to assess again the goodness of fit of a proposed structural model to the observed data. CFI compares the fit of hypothesized model to null model with no relationship between variables. It assesses how better the hypothesized model fit the data compared to null. Value range from 0 to 1. If the value for CFI is less than 0.9, then poor fit. Anything between 0.9 and less, and anything greater than or equal to 0.9 and less than 0.95 is marginal fit. As shown here in this table, the CFI value is given as 0.94. And as described here, has a value, the CFI has a value from 0 to 1. 1 show a very good fit, value close to 1 very good fit, and 1 represent perfect fit. The next index is the Bentler Comparative Fit Index, which is PCFI. Is a modification of the CFI that corrects for the influence of a model complexity on a fit indices. The value closer to 1 indicate better fit. There is another index which is Parsimony Comparative Fit Index, PSFI. As shown here in the extract, the table contains the ratio value, the BNFI and the PCFI. It is a parsimony adjusted measure, that's relative fit index that adjusted for the majority of indices. The ratio is parsimony ratio. It's calculate the number of constraints put on a model used to compute the PNFI and PCFI indices. PNFI is the parsimony normed fixed index, and the PCFI is parsimony comparative fixed index. Another index which is for the goodness of fit index, GFI and adjusted GFI, measure used to assess how well the hypothesized model fits the observed data. It evaluates the proportion of observed variances in the data that is accounted for by the model. So AGFI adjusts the GFI to account for the degree of freedom in the model. Interpretation of the GFI values. GFI and AGFI range between 0 and 1. Anything less than 0.9, poor fit. Between 0.9 and 0.9 and less than 0.95, adequate fit. Anything is greater than 0.95 is a good fit. Values of the GFI greater than 0.95 and AFGI greater than 0.9 is acceptable model fit, as shown here in the table. Shows that the GFI and the AGFI and the BGFI and the RMR. Another index which is the RMR stand for Root Mean Square Residual. Smaller the RMR, a value, the better the value for it. 0 represent a perfect fit. Another index is the normed fit index, NFI, and non-normed fit index, which is NNFI. NNFI, also known as Tucker-Lewis index, TLI. The values for NFI and NNFI range between 0 and 1. Cutoff for the value is equal to or greater than 0.95, indicate a good model fit. The next slide shows the table taken from CFA with the indexes for NFI, RFI, IFI, TLI, and CFI. TLI is Tucker-Lewis coefficient, known as Bentler-Ponent non-normed fit index. Range from 0 to 1. Value close to 1 represent very good fit. Value 1 represent perfect fit. For the NFI, normed fit index, also referred as delta, a value of 1 shows a perfect fit, and a value less than 0.9 can be usually improved substantially. The next table, the RFI, stands for relative fit index and is derived from NFI. Value close to 1 indicates very good fit, and 1 indicate perfect fit. For the IFI, incremental fit index, value close to 1 indicate very good fit, and 1 indicate perfect fit. The next index is the Archaic Information Criterion, AIC. It's a measure of the model fit that penalize model for their complexity. Lower values indicate better fit. So AIC often used for model comparison rather than absolute fit assessment, as shown here. AIC, PCC, PIC, and CAIC. It's measure the quality of statistical model of data sample to determine the model is the best fit for the data. The lower the value, the better. And another index is the Bayesian Information Criterion, BIC, is similar to AIC, PIC, also penalize model for complexity. Lower values indicate better fit. PC is also used for model comparison rather than absolute fit assessment. Shown here in this table, the PCC for Brown-Kodak criterion, BIC for Bayes information criterion, and the last one for consistent Archaic information criterion. And another index, which is the expected cross-validation index, ECVI, estimates the expected fit of the model to a new data. Lower values suggest better fit, as shown in the table here. The lower boundaries and the higher boundaries, and the MECVI is given. So there are plenty of indexes here, as shown. The NCP, non-collinearity parameter, with a lower and upper boundaries and a value to look at. In conclusion, for SEM, at least the following indices should be reported: the chi-square, the RMSEA, the SRMR, and the CFI. So there are many indices. Those are the major, the common, the most reported in the literature or when presenting the analysis. Another step to do when performing the CFA is to assess the factor loading by examining the values for the loading to ensure that they are significant and meaningful. High factor loadings indicate strong relationship between the latent factors and the observed variables. The next step is to examine the residual. Why? To check the residual to identify any patterns or outlier. Residual analysis help determine whether the model adequately expressed the relationship between variables. Another step to consider also model modification. Modification indices suggest potential improvement to the model. Only modify the model if it is justified. The 10th step is iterative process. CFA is often an iterative process to refine the model based on a result and a theory, and to rerun the analysis and to reassess the fit indices. If you find this video useful, do subscribe to the channel, leave any comment in the indicated box, and activate the notification bell to receive the recent and latest release into the channel of several different video clips, and click on the like icon and share the video link with others so the channel can expand and improve to include a large scope of different statistical method and how to analyze data using several different statistical packages such as SPSS, Excel, Stata, Jamovi, R Statistics, GraphPad, Prism, GPower, Python, and Mann. If you are a student or a researcher and you have a data, whether it is quantitative or qualitative, and you want to perform statistical analysis on that data using any of the softwares listed here, whether it's SPSS, Excel, Stata, Jamovi, R Statistics, GraphPad, Prism, Mann, GMP, Python, then do contact me to arrange for either a one-to-one private tutor session or a training course on any of these statistical packages. My contact details are given here, so don't hesitate to write to me or email me if you need a private one-to-one tutoring or a training course.